Okay, we are continuing on here on this chapter 14, which is our last organic chapter here. Last time we got into some of our final organic groups, including, I believe, the carboxylic acid. So remember, the carboxylic acid has the functional group of the carbon oxygen double bond and the OH group on it. Again, sometimes it's just sort of written COOH. And remember that this carboxylic acid group actually makes carboxylic acids, as we talked a little bit about, I think last time, really have the higher sort of boiling points, melting points, because it really does sort of have the ability to hydrogen bond with itself. It's got really two polar groups on it. It's got the oxygen hydrogen group, which is polar and really does permit sort of hydrogen bonding to occur. But it also has the carbonyl group there, which are carbon oxygen double bond, which is also polar, where the carbon's more positive, the oxygen is more negative. So really, when carboxylic acid, as we will probably see, but just in case we don't see it, let's take a look. When a couple of carboxylic acids actually get near each other, per se, we'll do that move there. Actually, we'll draw it this way. Draw it this way. It does permit basically some hydrogen bonding to occur between, for example, the hydrogen and the oxygen there. Also, another one could also sort of bond as well over here, between these two guys as well. So it creates really a lot of places where they can interact with each other and create sort of strong intermolecular forces, which will have them really the sort of highest in the boiling point and melting points. It actually, again, is one of the only things that can sort of beat alcohols in terms of boiling points is this carboxylic acid group. When we name these guys, because of that carboxylic acid group and that hydrogen that is at the end here, that means that it always must be at one end of the molecule or the other. You'll never find the group in the middle, the functional group. So really what that means is we're just going to count up, obviously, our carbons. That does contain, obviously, the carboxylic acid group, which is right here. So this guy would have 1, 2, 3, 4, and 5 carbons. Again, that would be based off of pentane. You could drop the E and it becomes pentanoic acid. As we talked about last time, you do not need to give the location of the carbon oxygen double bond because, again, it should be at the very end of that particular molecule. But if there happen to be other groups attached, like I think we saw last time as well, for sure, this carbon right here that is attached to the double bonded oxygen there will always be carbon number 1 in terms of numbering for everybody else. So whichever side it finds itself on, that should be carbon number 1. And then obviously in this case, we would go to the left here, right? 2, 3, 4, and 5. So although we don't need to include it in the name, it does still take the priority in terms of the numbering. And if we had any other group attached, it would be named and sort of numbered based off of that. So if I get rid of a hydrogen here, and again, if we had maybe just one hydrogen and a chlorine, this chlorine would then be at carbon number 4, and this would then turn into 4-chloral pentanoic acid. Any question on what we talked about last time, I think, with this? Also, I think saw it off of sort of a ring. And remember, if it is sort of off of a ring type thing, it will sort of, the entire functional group will really be off of the ring there. Although, again, this would be technically carbon number 1. We wouldn't use it for numbering. We would go to the ring and call whatever carbon there that's attached to the group number 1 there on the ring, in case there's other groups obviously attached there. So that's a slight variation of the numbering. Is if it happens to be attached to a ring, thank you. If it happens to be attached to a ring, you would obviously use number 1 on the ring wherever that sort of functional group is attached. Any questions on that there? Okay. So I think we left off, we finished there last time, yes, if I'm not mistaken. So I think we're here. Why don't you draw the line angle formula for 4-chloral hexanoic acid, and why don't you also do the condensed formula as well? And why don't we also draw, oh, I don't know. Let's do 3,4-dimethyl. Let's do heptanoic acid. All right, draw the condensed formula there for each of those, see what you come up with. So once again, always with the name, we're going to go backwards here. So really the oic acid part, it does tell us it's a carboxylic acid. The hexane part tells us it's 6 carbons. So once again, that's a good place just to start with, is to do your 6 carbons here. 3, 4, 5, and 6. Once again, since we know it is going to be a carboxylic acid group, you can put it on either side. I'm going to put it on the right-hand side there at the end is where it should go. Again, and either it's going to go on the right or the left in this case. That pretty much takes care of all that part of it. Now, again, since we have this functional group here, that definitely is going to be carbon number 1 for me. So I'm going to go 4 carbons over there to the left, and that would put a chlorine group there. So 1, 2, 3, and 4 there. What's left is like normal now. We just fill it in with our hydrogens. So this guy needs a couple. That one needs a couple there. This one just needs 1, a couple, and 3 pack there. Any questions on that one there? Now, if we were going to do the line here, again, it's 6. So like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. We could go down to an OH there and do a little bit of that. And we should still have 1, 2, 3, 4, 5, and 6. So again, this would be carbon number 1 here, and 2, 3, and 4 would look something like that there. Yeah. Any questions on that one there? Okay, then let us take a peek here at the other one I made up there. So this guy is heptanoic acid, so that's going to be a 7 pack. We'll go this way here. 1, 2, 3, 4, 5, 6, and one more makes 7. I'm gonna actually put my carboxylic acid group on this side because I ran out of room on the other side, so I'm gonna go that way with it. That works. So that takes care of that. Since I did actually put the group now on the left-hand side here, that obviously is going to be carbon number 1 for me in this case. In this case, carbon number 3 would be right about here where I should put a methyl group, and carbon number 4 would be right next door. I should also put a methyl group. At this point, we're just left with hydrogens. So we need 2 there. This guy needs 1. This one also needs 1. We need 2, 2, and 3 at the end. Any question on those drawings there? Now, if we wanted to do line structure on this guy, I guess we could do the same thing. We can kind of go 1, 2, 3, 4, 5, 6, 7, and do a little OH action there, and a double bond there. So that's going to be 1, 2, 3, 4, 5, 6, 7. So since I put my carboxylic acid group here, that would be number 1. which means 2, and that would be 3 right there, and that would be 4 right there. So it looks something like that there. Obviously, you get through it at the other end as well. Question on either of those drawings. Yes, sir. In terms of the numbering, is that what you're talking about? Yeah, no, it depends sort of how you draw it. So for example, what really determines it is where this group is located. So my first drawing here, it was on the right hand side. So that's the functional group. So it takes the priority. So wherever this carbon oxygen double bond is, that's always got to be carbon number 1. So I happen to do that. That's why on the bottom here, I actually put the group on the other side. And that's why carbon number 1 was over here, because of that carbon oxygen double bond. If I put it on the right hand side, like I did in the line structure here, that's why the carbon number 1 was on the right hand side. So it's wherever that functional group is located, and the carbon oxygen double bond part of that functional group will always be carbon number 1. So if you're drawing it, sort of depends whichever side you put it on. Then you would number everybody else accordingly. Yeah, the functional group is actually everything for a carboxylic acid, is everything in the box here. But since this is the only carbon that's part of that functional group, it becomes carbon number 1 when you're numbering. But yeah, but the actual functional group is actually everything that's in that box. Yeah. Other questions? You're welcome. Okay. So let's talk a little bit about some properties of these carboxylic acids. They're used as preservatives, flavor enhancers, also used as a preservatives added to cheeses, breads, and all those good stuff to keep everything going. As I talked about a little bit earlier and we did before, they are strongly polar because they actually do contain 2 very polar groups. And again, that carbon oxygen double bond on the carbonyl group is a polar group. And obviously our hydroxyl group is also very polar. As I mentioned, having those 2 groups is going to make it allow it to hydrogen bond really well with itself. And it's really going to increase those boiling points that we see. So I get also a hydrogen bond with water as well at both of those locations. So they are very soluble in water because of that. So when you got a carboxylic acid sort of interacting with water rather than itself, because water again is polar and this guy is polar, the water has an ability to interact with the OH part of it. But because this carboxyl group here, or carbonyl group, I'm sorry, is also polar, the water can also interact over here as well. So they can interact in both of those places, giving a pretty good solubility. So upwards of like 5 carbons are very, very soluble in water. So up to pentanoic acid should be fairly soluble in water. But like everything else, as we talked about, as you sort of build out more and more carbons and hydrogens, the solubility does start to decrease as you kind of go past sort of 5 carbons, for the same obvious reason that, it's just going to be a lot harder for everybody to get in there, especially water. So you can see here our first 5 are soluble in water. When we get to 6, we're still slightly soluble at this point. Slightly soluble usually leans towards being almost insoluble. So the degree of solubility does decrease a lot. And then if we have some big type group like a benzene ring hanging off of there and benzoic acid, again, it just sort of gets in the way of some nice interactions that occur. Because they are obviously acids, they basically can do an acid-base reaction. A lot of carboxylic acids are weak acids, like we talked about acetic acid before, which is actually ethanoic acid, but it will do a basically acid-base reaction. You could do it with water, like a Bronsted-Lowry definition, where it will donate its H plus over. And as you can see on the bottom there, it will create H3O plus, and it will create some acetate, which is this guy here. It also obviously could just react with a regular base, like something like sodium hydroxide. So if you took some acetic acid or ethanoic acid, once again, it will do a really normal sort of acid base reaction. It's going to really donate over here. It's going to be the H and the OH there that's going to make water. And then we would get some sodium acetate. I'll just write the formula instead of draw it there. We'll use the sodium acetate that will basically will come on to the back part there. So all carboxylic acids basically could follow pretty much an acid-base reaction, like we talked about in the acid-base chapter, where it will donate its H, and a lot of times may make water if it's reacting with an actual base. It will make H3O plus if it's basically just dissolving in water like it did up here. In this case, obviously the water was acting as the base, and this guy was obviously acting as the acid in that particular case. Also, as we talked about, weak acids or weak electrolytes. So, if you see it sort of dissociated, those are double arrows that we saw before with weak electrolytes that come up in the reaction. So write the balance equation for the dissociation of butanoic acid and water and identify the carboxylate. So let's just go through it together. So we'll start with butanoic acid. That should be 4 carbons. And obviously here we would put our carboxyl group here, carboxylate group. This obviously here would then fill in hydrogens as there's nothing else attached in that name. And it's going to react with water in this case. So again, this is going to be our acid. Water is going to act as our base. So it is always this hydrogen here that's attached to the OH group that basically participates in the acid-base reaction. It's that hydrogen because it's part of that polar group, which makes it kind of easier for that hydrogen to come off. It's never the hydrogens on the carbon in this case, always the hydrogens on the oxygen when it's doing an acid-base type reaction. That guy's going to send over there. And the result of that is here we will make H3O plus as it gains that guy. And what's left is everything over here except for the hydrogen, basically. So it's going to be everything exactly the same, except that we will just take that hydrogen off. And when we take the hydrogen off, it does gain a negative charge, and that is what is known as the carboxylate ion. Carboxylate ion is basically this part of it. It's a carboxyl group without the hydrogen. Basically, it lost the H plus and it makes a ion that is there. Any questions on that reaction there? We obviously talked about how to produce these as well, I think last time. And again, that is from really your double oxidation there of your primary alcohol, right, to your aldehyde, to your carboxylic acid is again how we basically produce these guys as we talked about. And there's the prettier picture, I suppose, of the one I drew. All right. Now, it could also obviously do neutralization reactions, as I kind of jumped a little ahead there a second ago, but it's really just an acid-base reaction. So if you have any of these carboxylic acids, obviously it will maintain its acid form there. It will react with the base. And really, just like we talked about when we make a reaction between an acid and base, we basically make water. And just like we talked about when we did it, once again, it's going to be the H from the acid and the OH from the base is going to come together to form the water that we see over here. What is left is the other two parts come together, and that's what's sometimes referred to as a salt. So if you remember when we talked about acid and bases, that's basically the two things you get when you react an acid and base together is salt and water. And Again, when this guy loses that H, he becomes negatively charged, which is displayed here. And obviously the sodium, when it goes away, becomes positively charged, and those two guys are attracted to each other. And that makes what is known as sodium formate in this particular example, but it's basically the salt that is there. This is really still a double displacement reaction. Basically, the two positive guys switch partners. The H and the sodium basically switch partners, and you get what's on the other side there. Any questions on that there? We're not going to worry about the carboxylate ion in terms of how to name it, but we just kind of put 8 at the end of it. But here we'll just look at the reaction one more time. So this is our carboxylic acid, which obviously is our acid. This is KOH, which is a strong base. So once again, we're going to take the H from the acid, the OH from the base, and that will again give us our water on that side. And if you look at this, you could clearly see, hopefully, that pretty much everything else remains exactly the same over here, except that it obviously does gain a negative charge as a result of losing that H plus. And then our potassium also comes over here to make our salt. So carboxylic acids, again, basically will do an acid-base reaction, produce a salt and water. Any questions on that? All right, so let's go to here. Write the balanced chemical equation for propanoic acid and sodium hydroxide. Why don't you give that a go, see what you come up with. So if you're not sure, you should be able to, at this point, draw a propanoic acid. So propanoic acid definitely would be 3 of them. Oic acid tells us it's obviously a carboxylic acid. So this guy, kind of filling in our hydrogens there, should look something like this. We're going to react it with sodium hydroxide. So again, really an acid-base reaction happening here. Once again, we're just going to take our hydrogen from our acid, our OH there from our base, and that is going to make our water. And basically, we're just going to put together what's left at this point. So again, nothing else changes on the propanoic acid, except that obviously we got rid of the hydrogen at the end. That again makes it a negative charge as it loses that H plus. And this guy here, obviously, when he kind of goes away from the sodium hydroxide, does have a positive charge. So you could just write it like this. If you sort of drew out what's going on there. If you just wanted to write the reaction, you could just write CH3CH2 COOH plus NaOH H2O plus some Na CH3 CH2CO and stuff like that. So that would be right now. Yes. Like here or there? Yeah. It does not. As long as it's on that side of the arrow, it's all good. Yeah, it doesn't really matter which one comes first. Questions? Okay. All right. We'll get to that later, I think. All right, let's talk a little bit about esters at this point. So esters is another group of organic molecules, and esters are very similar looking to carboxylic acid, except that they do not have the hydrogen. So they have kind of an oxygen then connected to a carbon type of move there. Should be the functional group. So very similar to carboxylic acids, which we've just been talking about there. And as you might imagine, that is basically how we make an ester. Is a carboxylic acid is part of the making of an ester. Esters have a lot of smells, if you will. They make up a lot of smells and flavors and that type of stuff. is a result of certain esters that are made. I think that's the experiment. Maybe this week you'll make some and you're supposed to smell them. I think they used to do years ago. So again, they really are synthesized from a carboxylic acid and an alcohol. So how we make an ester, as we will see shortly, is through what is known as an esterification reaction. And basically we make it by taking the carboxylic acid and adding it to an alcohol. I'll draw the rest of everything, but the main part of this reaction is basically we just sort of make water. You know, we just kind of grab out water there. We sort of grab out water and then kind of squeeze everybody else together to make the ester group. So water comes out and squeeze everybody together and you get this ester functional group that occurs here. So they are definitely related to each other because that's basically how you make an ester, is from a carboxylic acid and the combination of alcohol. As I mentioned before, they are responsible for a lot of smells that we are very commonly familiar with, things like bananas, oranges, strawberries, and so forth. We'll see more of that reaction in just a second here, which is right here, actually. So we will look at this reaction here. We're going to take our carboxylic acid, and in the presence of a acid catalyst, which is what the H plus stands for, and a little bit of heat, we basically are just going to kind of take out water and put together our alcohol part as well. So I might have highlighted the wrong O's and all that on the last one, but you get the same idea here. This is basically just going to go out and then just basically squish everybody together to get to our ester, which is right here. So as you can see, the nice thing about this is, frankly, you just take the water out and you copy left to right there, everything that's there. So CH3, COH, that is all still there. And then take out the water and attach the other part to it. And that gives you your completed ester at that point. How we name it is, as you might be able to maybe determine there, is we basically kind of use the O here as our boundary. And the carbons that actually come from the alcohol, which would be this guy right there, is only one carbon. So we name it as a group. So one carbon is a methyl group. Now the carbons that basically come from the carboxylic acid, which are these two right here, is based off of ethane, gets like the O8 at the end of it, and this becomes methyl ethanoate. Again, the ethanoate is the two carbons as part of the carboxylic acid part, gets the O8. And again, the other guy that comes from the alcohol gets named as a group, basically. Any questions on that there? So here's an example of a reaction. We take ethanoic acid with one propanol to make a ester called propyl ethanoate. I'll spit that out. So once again here, if we look, this is our carboxylic acid. This is our alcohol right there. And once again, we're just going to simply take out the water, the OH from the carboxylic acid, and the H from the alcohol, and then basically just squeeze everybody together. So I'll just put checks next to things. CH3 is the same. Carbon oxygen double bond, carbon oxygen double bond's the same. We're going to skip this part when we draw it on the other side, go to the oxygen next, the CH2, CH2, and CH3. So again, you're essentially just taking water out and pushing everybody together. Once again, you're not going to make any fancy moves or anything like that. It's all going to stay the same. Question? Yeah, the water comes out of the two molecules that are really making the ester. So out of the carboxylic acid and the alcohol. Water comes out by itself, so it's formed as a result of that. But to actually make the ester, carboxylic acid, alcohol, take the water out, and then basically push whatever's left back together, and that will get you to your ester. Again, in terms of the name, what we want to focus in on is, like I said before, sort of that oxygen that comes from the alcohol, which would be this guy. And if you're not sure which way you should go to find the one that is part of the alcohol, if you have an ester, it's always away from the double bond is the alcohol part. And that would give us 1, 2, 3 carbons as part of the alcohol. So that gets named as a group, which is where the propyl part of the name comes from. Now going the other way, basically towards the carbon oxygen double bond, starting with that carbon, gives us 1, 2 carbons, which is where the ethanoate comes from. You just add basically O8 at the end of ethane. Question on that there. Once again, in this case, you don't have to give any type of locations where the carbon oxygen double bond is, but obviously that would be sort of the lower number that you would want to if there's happen to be anything else attached. All right, so write the balance equation for the reaction of propanoic acid with methanol. So see what you come up with. Okay, we'll start with just drawing things correctly would be good. So propanoic acid, again, is a carboxylic acid. That's the oic acid part of it. Propane is 3 carbons. And I'm going to put my carboxylic acid over here on the right. Once again, you could do it the other way, but since we're writing a little reaction here, it might be helpful to have it over there. Plus our methanol is 1 carbon. And obviously, that one on there, that is CH3OH in this case. Now, you may not want to draw it in this situation like that. You may want to turn around so that the hydrogen and the oxygen sort of face in the right way, since we know we need to kind of take out water anyways. And it just might help you more visualize what you should do and allow you easier just to kind of put everybody together. So obviously, since we know when we have a carboxylic acid and an alcohol, basically out goes water, basically, right? So that's, again, a good thing to remember. And blank the screen. All right, let's try that again. So once again, here, we're going to take out the water, and we're going to go just like that. And that's going to take out our water. And then basically what is left is we're just going to frankly copy left to right and just take out the water and squish everybody together. So I'm going to draw it down here since I ran out of a little bit of room. There's no arrow needed to actually, but it's just drawing it down there. CH3, CH2, C double bond O. That takes care of everything on this side of the water. Now to go to the other side of the water, which creates our ester bond right there. Again, this being sort of our ester sort of functional group there, gives us this guy right there. Any questions on that there? Yes, sir. What's that? Yeah, so all this would be probably 1 straight arrow for asking. Yeah. The only time you would probably use 2 arrows is if you had like a carboxylic acid by itself, you know, would be it. Now, in terms of naming this, if we wanted to name this, once again, we would kind of look at this oxygen as our starting point, if you will. Going away from the double bond will give us our alcohol, and that is sort of the first part of the name. So that's obviously just 1 carbon, which would be a methyl group. Now, going the opposite way towards the carbon oxygen double bond would give us obviously our carboxylic acid part, and that has 1, 2, and 3, hence the name here. And that would then become propanoate, O-8-T at the end of it. So there's 2 ways to sort of remember the naming part of it is, right there. I personally put O8 and just drop the E off of propane. Some people will tell you to go off of propanoic acid and drop the IC and put 8 at the end. So whichever way you want to do it, it's fine. But I just remember 08 and go off of basically the alkane name and drop the E, and I'll get you basically the right name. But some people will say just drop the IC off of here in the acid and then put 8 at the end of it, and obviously it gets you the same name. So whichever way you want to remember it. Any questions on that there? So this is a esterification reaction, which I think is what you will be doing in the lab this week. Again, put them together and try not to smell too much of it all, I suppose. So let's talk about the naming of esters as we sort of got ahead there and started naming them. But officially, the way we do want to name them is, like I said, you want to always, kind of locate that oxygen there. And again, going away from it would be your alcohol, which is named as a group. So like a propyl, obviously a methyl, an ethyl, whatever it may be. Going towards the carbon-oxygen double bond would be your carboxylic acid part. And like I said, personally, I go with the alkane, drop the E and put 08 at the end of it. So again, if you want to do drop the IC and put 8 at the end of it, you could do that as well. Obviously, you drop the acid from the carboxylic acid name. So looking at this one here, we have our methyl group and our 2 carbons here. So again, methyl ethanoate in terms of our answer. And again, that comes from really methanol and ethanoic acid would be the 2 things that come together. In the parentheses here is the common name. We won't use the common names, but that's what these are the parentheses sort of represent. And again, some of these do have common names, but we will focus more on the IUPAC way of naming. So if we look at these guys here, once again, going away from the double bond there, that is our alcohol part, which is actually an ethyl. Going towards it is our main part of the name, which is also 2. So that is ethyl ethanoate. Here is the one we just did. I think we got our methyl going again away from the double bond. Going towards the double bond gives us 3, which again would give us our methyl propanoate. I would say probably maybe the only common one maybe might be the easiest would be the one maybe with benzene involved. And in this case, going again away from the double bond gives us our 2 groups from the alcohol, which is ethyl. And then obviously this is benzene and drop the E and put 08 at it, and that's benzenoate. Any question on any of those names there? Okay. Salicylic acid, aspirin, is a ester, as you can kind of see here. There's our ester group hanging out there. It's a fun lab. Sometimes in chemistry, you get to make that. Oil wintergreen, I almost think you make that one in lab, maybe. Also, again, our ester group here. And again, here, even though it's sort of a benzene ring, it's still the same sort of thing that occurs. It is just this water that's going to come out here. And basically, this guy will go up there. So that's the alcohol part that goes up there. As you can see here, everything on this side is exactly the same. It stays the same down to this guy that hangs out over here as well. So nothing else changes in this particular reaction. All right, so why don't you write the name for the following ester? Okay, let's take a look. So obviously we see ester groups here, and that's really, if you have the picture, kind of where you want to focus is right there. Actually, when you're drawing it as well, that's where you want to start as well. So we want to focus in really on sort of that part of the functional group there. And remember that we want to start with really the part that came from the alcohol, which means we're going away from the double bond for the alcohol part. That is 2 carbons, which means that would be an ethyl. Now going the opposite way would give us our carboxylic acid part, and that is 1, 2, and 3 carbons. So 3 carbons would be based off of propane, and we'll drop that E and put 08 at the end of it. So that would be ethyl propanoate. Any questions on that name there? Same thing on the next one that I drew. We're going to start with the alcohol part, which once again is away from the double bond there. That gives me a 1, 2, 3 carbons. So 3 carbons should be propyl. Going the opposite way towards the double bond, not forgetting to count that carbon that's there. 1, 2, 3, 4, and 5 carbons. So 5 carbons would be based off of pentane. You're going to drop the E and put O8 at the end of it. So that would be propyl pentanoate. Any questions on either of those names? Okay, so what I'm going to do then is draw the top guy, which I see hexanoate, which tells me when I see the O8 that it is an ester. And I would say in drawing esters here, maybe that's a good place to start with, to be truthfully honest with you. So the part that I highlighted in the other two is really part of the functional group there, where I'm going to start my drawing basically. And now that I have sort of the functional part of it, I could do really the same things I do when I name it, which is if I go away from the double bond there, that should be the alcohol part, which should be named as a group. And I see a pentyl, which means there should be 5 carbons basically there. So that's what I could do, just put 5 carbons. 1, 2, 3, 4, 5. Going obviously the other way is where our carboxylic acid should come from, which is from here, which is hexanoate, which is 6 carbons. I got to remember though, in this case, I actually do have a carbon to start with, right? So that would be 2, 3, 4, 5. Oh, should have went smaller. 6 there as I run out of room. Let me kind of redraw it underneath. So actually, want to go up on top there. We can see it. Get rid of this here. All right, so I'm gonna redraw that up high so I can actually see what I tried to squeeze in there. All right, so again, we had 6 to the left there. 1, 2, 3, 4, 5, and 6. We had 5 to the right, 2, 3, 4, and 5. Not sure I ran any better there up on top. Everything else will obviously be hydrogens. So we'll stick our hydrogens in there. And we'll end up with something that looks like this, I think. So hydrogens all the way across to get everybody to 4, obviously, in that case there. Any questions on that particular one there? So once again, we got 1, 2, 3, 4, 5 for our pentyl that was there. We have 1, 2, 3, 4, 5, 6 for our hexanoate. So pentyl hexanoate. Yes. Any questions on either of those two there? Just pick smaller carbons is really the better move, I think. All right, what is the name for this one? You don't have to worry about the common name. So just what is IUPAC name for this guy? Okay, so once again, we want to kind of focus in here on sort of the functional part of it, especially the oxygen there. And once again, going away from the double bond is our alcohol part. And that gives us 1, 2, 3, which is named as a group. So that is going to be propyl. Going towards the double bond is our carboxylic acid, which has 1 and 2 carbons there. So that is a little propyl ethanoate at the end. Any questions on that one there? Yes, sir. No, it just happens to be that's the way it's drawn. So, you know, for example, if this was drawn like this, so in this case, we would still focus in on this oxygen. And once again, going away from the carbon-oxygen double bond is going to give you that first part of the name, which is the alcohol. In this case, it's obviously the same. And then going towards this would give you the carboxylic acid or the base part of the name. So it could definitely be drawn the other way around. So that's why I refer to it as not going right or left, but really going away from the carbon oxygen double bond will always put you in the right way to get the alcohol part. And then if you go towards the carbon oxygen double bond, it will get you, whichever way that is drawn, it will get you towards the correct part for the carboxylic acid. Other questions on that? So as I mentioned before, esters definitely fragrances, perfumes. Small esters are volatile, which means they do go into the gas phase really easily, which is why you could smell a lot of it because it is fragrance and stuff like that. They are also soluble in water, small ones, really big ones, not so much because, again, too many carbons involved. But here are some esters from a table, and again, responsible for things like pears, bananas, oranges, pineapples, all that good stuff. But again, in this case, going away from the double bond is going to give us our group name, or that goes from the alcohol. And again, the top one there is our propyl ethanoate, responsible for pears. Here's our 1, 2, 3, 4, 5, which is our pentyl ethanoate, responsible for bananas and so forth. So again, whichever way that carbon oxygen double bond, you want to go away from it first to get the first part of the name, and then get the base of the name, you want to go towards it in that particular case. All right, so I want to draw a couple of these here: 3-bromol butanoic acid and ethyl propanoate. So again, on the first one, I see oic acid. It's actually a carboxylic acid. So I got butanoic acid, which should tell me I have 4 of these carbons. Because this carboxylic acid, again, you could draw it on left-hand side, right-hand side. Again, here on the right. That takes care of all that there. That's obviously carbon number 1 because of the way I drew it, which is carbon number. And then obviously we just need to fill in our hydrogens here. And that should do it on that one there. Any questions on that? This one is 08, which tells me it is a ester. So again, as I talked about, sometimes easier just to start with the ester group when you're drawing these. So again, you just need to kind of remember this is the main part of that functional group. And now we know, once again, as we've talked about, that we go away from the double bond is our alcohol and really our group part of the name, which is this guy. And that's ethyl, which means there's 2 carbons. So I'm just going to add my 2 carbons. And then obviously going the other way is our carboxylic acid part, or the main part of the name here, which is based off of propane, which should be 3 carbons. Again, I want to remember, though, that I already got a carbon drawn there, so I don't want to draw 3 more to give me 4, right? So I just need to get me 3 total going that way. And now, just like everything else, we're just going to fill in our hydrogens there. So that one needs 3. This one needs 2. That one needs 2. And that one needs 3 in that case. Any questions on any of those there? All right, let's see. Let's talk a little bit about another reaction that esters undergo, and they are hydrolysis reactions. Hydrolysis reactions basically just means we're going to throw water in there, basically. And you can probably imagine what's going to happen in this case, since we take water out to make it. When we throw water back in, it's basically just going to break back apart into the carboxylic acid and the alcohol. So it's kind of the reverse of the esterification reaction, is the hydrolysis reaction. And there's 2 types of hydrolysis reactions that occur. One's an acid hydrolysis and one's a base hydrolysis. So let's take a look at the acid hydrolysis first. And the acid hydrolysis is done by adding water with an acid as a catalyst. That's what the H plus on top of the arrow basically refers to. And just like when we put it together, we basically are going to break it apart just exactly in the same spot, basically. And when we do that, let's draw a little higher here, maybe. So once again, we're going to break it apart exactly where we put it together. And really what's left is in an acid hydrolysis, you get back the carboxylic acid and the alcohol exactly the way it was before. So you could think about this one of 2 ways. We could just draw the 2 parts separated, basically. And then basically we just need to make a carboxylic acid and an alcohol. So to make an alcohol, the guy on the right needs just a hydrogen, right? So just gotta add in a hydrogen. To make the carboxylic acid on the left, he needs an OH at the end of there. And that is these two parts actually coming in. So in that case. So in an acid hydrolysis, you're basically gonna add water, you're gonna break apart the ester, and you will get back the completed carboxylic acid and the completed alcohol. And again, you can just separate them like you put them together and just basically finish them out. Get the alcohol back to an alcohol by throwing an H on it, and get the carboxylic acid back to obviously a carboxylic acid by putting the OH. It's basically the perfect opposite reaction of putting it together in the esterification reaction. This is basically putting them back apart. Any questions on that there? Now, a base hydrolysis also has water, but it involves a base like sodium hydroxide here, as we can see here. Now, in a base hydrolysis, we actually do not get back the carboxylic acid completely. We do get the alcohol back, but we don't get back the complete carboxylic acid. And if you just want to keep track of something like this, for example, we'll just take a look here at this here. We'll go this way. CH3, C double bond O, OCH3, and then some NaOH. So in this particular case, same thing's going to happen. We're going to break it apart right there, just like we did before. We're going to draw both parts. And then I'll just draw it down here so I don't run out of too much room here. And once again, we do get the alcohol back here. So you can make your alcohol like you would. And we will take the H. And if you think about that, that is like kind of right there if you want to think about it that way. Now, the problem though is, right, I don't have an OH left to make my carboxylic acid. I got like an oxygen and a sodium left. And really the only thing I could put on there is the oxygen and the sodium here. So what I get back actually is a carboxylic acid salt and an alcohol in this case. So we actually get back a salt of a carboxylic acid and we get the alcohol back. So that is the main difference between the two hydrolysis reactions. They both essentially break apart the ester, but it's only the acid one that will actually get you back both things completely like it was before, the carboxylic acid and the alcohol. When you do a base hydrolysis, so it's sometimes referred to as saponification reaction, which is a fancy way of saying you just made soap if you do it correctly. It's basically how soap is made, except soap is like a lot more carbons and hydrogens, a big chain of carbons and hydrogens. But this is basically how soap is made. So by using a base, we don't get the acid back, but we do make the salt that happens there. And we'll talk about soap in a later chapter as well. Any questions on those two reactions? So why don't we try one? Write the balanced chemical equation for methyl. We'll go with methyl ethanoate here. There you go. When it reacts with water, heat, and acid catalyst and potassium hydroxide, which is a strong base, and some heat. Okay, let's take a look since we're getting to the end. We'll start with methyl ethanoate. Once again, it is an ester, so we'll start with the ester part. Again, to the right there, my double bond should go methyl, which is 1 carbon. And the ethanoate should be 2 carbons on the other side. And I already got 1, so that should be our starting guy there, actually in both of these. The first one, we're going to add some water here with a acid catalyst that tells us, okay, it's water and acid catalyst. I should get back both things exactly the way they were to begin with. So once again, we're going to break this guy right between here. And we're just going to draw the 2 parts there. And that would get us our CH3, C double bond O plus an OCH3. And here we just need to make back our alcohol and our carboxylic acid. So the H will end up over there to get our alcohol, and our OH here will end up over here to get our carboxylic acid. Questions on that one there. Now the second one, which again is starting in exactly the same thing, obviously. Except here we're adding KOH, which is obviously a base hydrolysis here. It is going to once again break apart there. We're going to draw our parts like we did on the other side. And now we need to remember that when we do the base version, we don't get the carboxylic acid back, but we do get the alcohol. So we can throw our H in there if you like, there to get our alcohol. And if you want to think about it this way, it's not 100% correct, but you can think about the H came off of there, and that leaves me an oxygen and the potassium. Knowing that this is really like a carboxylic acid, I know the oxygen should always be the guy attached, right? And that will be a negative charge, and then this guy will be a positive charge, and that would get our salt and obviously our alcohol back here. Question on either of those two there. Okay, we will lay it up there.